Alright, I believe we're recording. I'll just accept that we are. Well, I better check. Okay, we are. Anyway, so this the Cindy guy's made another video, and I think it's an older video that he's reposted or something, just because he talks about the new year. But anyway, somewhere in there. It's not a bad video in terms of getting to some points about how photons are detected, so I thought I would use it as fodder for a conversation. And the fact that this is all stuff physics doesn't do, any of this fundamental science. They're just given up on all doing any kind of fundamental science, and they just do all this abstract, fancy bullshit, entanglement crap, quantum computing, all this other mush. And all of this fundamental science is just left, unloved. And to me, that's a real commentary on physics. Because these are really interesting questions. Getting to the truth. What are these photons? Is it a wave? Is it a particle? They've had this duality for 100 years, and they haven't been really compelled to sit there and try to answer the question better than they answered it 100 years ago. They just want the same evidence, almost. I'm not saying there aren't some people working on some kind of technology to try to be more explicit and gather more information, but it's just that the amount of effort put towards the task is infinitesimally small compared to other avenues of interest. So this whole I don't agree with this Cinti guy at all. I think he is a some sort of ether wave nutter. Sorry, just cheap rhetoric, I know. I just don't see any reason to play with all these phantasmagorical ways of looking at the universe, where all this movement happens and all this interaction is happening, and you've created a small universe that's more complex than our world almost. It's the elemental universe has to be elemental. It has to be simpler. There's no other way to look at it that I think is rational when you put all the evidence together. It's the only rational way to look at it. It has to get simpler because complexity would be visible. The dependability of systems is just so obvious. Just as I pointed out, the fact that a carbon atom and a carbon atom and a carbon atom and a carbon atom, they have to all be the same. They can't be different things. They can't have vagaries and crap built into them. And we even see it in radioactive decay. As chaotic as that looks, it's really precise too. I mean, it's clearly, in my opinion, a clear evidence that the atoms aren't from the same place, and that they're different ages, and they're decaying by a certain rate, each one. And some are old atoms, and so they drop dead right in front of you, and some are younger, and they don't drop dead right in front of you. That kind of thing. But anyway, even if you don't believe that, I'm just saying there's very reliable systems. We can't have reliable systems if things can be fat and thin and tall and short, and all of that diversity would not make for a dependable, reliable system, as we see in our in the world today. So anyway, let's play some of this, and I'll just raise the obvious. They're not obvious, obviously, because nobody else is raising them, but I just mean they're points that just haven't been addressed, and how we understand what a photon is, what interference is, what patterns are, mechanisms, and again, some of the points he makes in this video are really good, talking about how our detection methods leave some doubt about how the thing's functioning.
Hello, welcome to Debunking Particle Wave Duality. Physicists believe that light behaves both as a wave and as a particle.
I don't know what they believe, so that's another tricky word, right? They've obviously they back into it. So it's like these different people will quote Einstein when he's making his concession statement, where they basically forced Einstein to accept quantum mechanics in its form. And so he made a little statement saying how, yes, well, it kind of obviously does this thing and blah blah blah. But it's clear that Einstein was uncomfortable with the idea of waves. you know, so they've accepted a duality because why? Why have they accepted it? That's a good question, because I guess they just don't, they gave up. And they apparently said, well, our best guys can't figure it out, so therefore it can't be figured out. So let's just accept a stupid answer. And that's what they accepted, as a silly compromise. They did a political thing, which scientists really aren't supposed to do. They aren't supposed to do political compromises. And that's what they did. Instead of saying, let's leave this door open because we just don't know what the hell this is, and they just wouldn't admit it, so they pretended, let's everybody, and they wanted the quantum mechanics to be interesting, so they jumped on that bandwagon. Let's make it interesting and spooky. We like spooky action and such. They wanted that world. So anyway, too much commentary. Sorry.
They have named this particle of light the photon.
Well, okay, they didn't really name it, so we know that everything got named and got assigned back in, you know, somebody has to do that stuff, and they do it when they're not fully informed. So Benjamin Franklin got plus and minus wrong. You can go through all the list of stuff that they screwed up. And obviously, at first, they're thinking of a photon as, okay, it's a clump of stuff that travels and hits. Then they find out it has a frequency, and so then the clump gets kind of complicated. You know, because, you know, you're thinking about a mile-long clump doesn't really work for a radio wave or something, and, you know, and they didn't like the bullet idea at all. So, you know, as much as people claim that these people are particle physicists, they hate particles. They despise them. I mean, even Einstein didn't talk about these things as bullets, separated by a distance, because they hated the idea that, oh, what do you mean, it's little rocks? You know, that's all it is rocks at a frequency? No, they didn't do that at all. No, none of them. I haven't seen one paper, one thing ever written that talked about a photon as being corpuscles at a distance. Even Feynman, when he says it's a corpuscle, he's talking as if the whole ray is a corpuscle. He doesn't even get the, no, individual clumps of energy. Corpuscle. So this is the part where I should draw these distinctions, just to what? just to try to make it clear of the choice here. Okay, so, you know, we know that waves create a problem in the sense that you got to create some kind of fieldy wave. So they invented, I'll just draw it in some kind of bullshit. And, you know, they created this transverse whatever blah 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 twisty idea of what a photon is, that somehow it's wreaking energy in two different fields. Okay, there's two fields, the electric and the magnetic, and somehow it's being pushed and pulled by those fields, or it's pushing and pulling on the fields. Now, there's no evidence. We've never detected a photon indirectly. I mean, there's no evidence that you can sense one of these things went by. Like a photon just went by me because my hair moved a little from the photon wind in the field. The field perturbation spread to me. So there's no evidence that this wave goes this way in any way. It has a one direction, and it has a very tiny profile. And then they even take, you know, something like the frequency, you know, the frequency part, yeah, so, and they're making it go in a you know, very discrete location. They've just taken, you know, they have this idea that it's a wave, but it's a wave that somehow has confinement, you know, that doesn't spread this way at all. You know, the waves aren't waving, you know, big waves. There's no, you know, it doesn't go the way regular waves move at all. And it clearly doesn't do it in, like I said, these tangential or perpendicular perturbations don't exist through any experimental observation. There's just no experiment demonstrating it could be that way. So anyway, but they still believe. So they believe in some kind of wave that just stays confined, you know, and moves in a direction. And none of them, like I said, I've seen no description by any particle physicist who says this is a photon. Okay, it's just clumps of momentum, in the sense that if it hits something, it's going to affect it. So if it hits an electron, it's going to move it, it's going to exchange its momentum, and it's we can possibly detect that. So I've seen no one draw that picture. And that's the picture I had at whatever, 12 years old or whatever it was, 11. Okay, when I heard the word photon, this is what I always thought of as a photon. It's a clump of stuff. And I didn't really think about the ray part of it, but that's sort of a significant part of this whole conversation. Is it's not only about how close together these bullets are that would define its energy. Obviously, photons this far apart are going to have less energy in them than ones that are closer together in an amount of time. But the part I didn't think about was the fact that these clumps of photon, okay, see, so they're calling this whole string of stuff a photon, and that's where the word gets kind of deceptive, because it's even when they have them in this wave form, the waves are not a photon. It's like there's a clump of waves, there's a array of waves, and that's how they're emitted by electrons, frankly. And so that ray can be different lengths. It doesn't have to be 10 clumps or 15 clumps or 2 clumps or 1 clump. I mean, obviously one clump, it can't be at a frequency, so we know we're not going to see a 1 clump photon, and maybe at best we can see a 5 clump photon. It's clear our eyes can only receive a pretty substantial clump of energy. It has to be hit by more than one for our eyes to recognize it. Now, other animals' eyes can recognize smaller hunks of photon. But again, it's a ray, it's an amount, and so we have this word that's just totally inadequate to the conversation, because what would really be the photon? Is the photon the element that makes the photon, or is the photon two of these things? You want to call that a photon, or is a photon any number of rays of these things, which ends up giving it different energy values, which just makes things confusing. Instead of recognizing the quanta, the bits, the bullets have the same amount of energy, and the question is you can affect things differently by shooting bullets slowly or shooting bullets fast. And I've pointed out that gets the whole tipping argument. You want to tip something over, you've got to hit it at its resonant frequency to knock it over. And the same argument could be made for the photoelectric effect, is that if you want to release a cold electron from a surface, you got to hit it, okay, and nudge it out. You got to get moving, and then it'll fly out. So you got to give it more. You got to get it to absorb the energy and keep reflecting it, so it pops out, because you've stored each photon that hit. That energy was stored in the system, and that's what happens when you hit something at the right frequency. You store the energy, so you can get more and more energy into the system. And finally enough energy to break it, and that's the idea. And so the photodetector works on that principle. So that's the one thing, this device they had for the photomultiplier. And what it basically is doing to say I see a photon is it just takes a bunch of these electrons and it heats them up, throws a voltage through something, and gets them really sensitive. So they'll, if you want to make it really sensitive, you pump it up with 200 or 300 volts. You get these electrons where they're even popping all by themselves, like they're so ready to pop into another surface, and that's how it works. It basically reflects them back and forth, and each time it hits the surface, it knocks more stuff loose. So it amplifies it amplifies one disaster. So it's like having a spiral of dominoes, and you just hit the one in the middle and all of them fall out radially or something. It just makes a small amount of energy into a big amount of energy. It just amplifies the disturbance by making it very sensitive. Now they can make it very sensitive, but then there's this problem, because then they just sort of almost spontaneously, it's not spontaneous, but it's almost spontaneously, fly off the surface, and so you can't tell whether, you can't separate the noise from the signal, because you got so much random noise in the system. But they can tone it down and tone it down. They get it to a system that's pretty, they can see photons we can't see with the device. So the device is much more sensitive than our eye is, so it catches these little rays. But clearly it still can't catch one little an independent little ton isn't going to be able to do much, then I'd say that's almost in the form of gravity. So it really can't detect gravity. Well, that says it can detect it, but it can't resolve an image of it. It can't do anything with its detection because it's too small a sample. It's got too small a pupil. Can't see enough of the world to resolve any images. But that's basically the system. So yeah, all the best we can do is say a photon is this minimum amount of energy. It has to be two things at a distance, and we could argue that it might take 3 or 4 of those just to even knock an electron free. Even an excited electron that's ready to jump loose, it still needs a couple of hits to get it free, and that might be what you need just to get over the amount of noise in the system, in the sense that you got cosmic rays coming in, X-rays, all kinds of other photons that are going to mess up your ability to resolve anything with your detector. Alright, so that's probably enough of all that crap. Yeah, probably enough. Alright, back to the video and such.
I'll show that physicists have inappropriately ascribed the corpuscular nature of their instruments to light.
So he's saying that somehow the instruments are forcing things to be corpuscular, and clearly they're forcing them to have a certain amount of momentum transfer, and so that's pretty good physics, pretty reliable information, is that this stuff does come in clumps, and that it comes in packages. It doesn't come in some kind of varying thing where you can have a half a photon or a quarter of a photon or an eighth of a photon, that kind of thing. It doesn't function from the results of many experiments. It does have a Planchness to it. You have to have multiples of a minimum, and that evidence exists.
I'm going to show that for both the image intensifier version of the experiment as well as a photographic version of the experiment. I'm going to show you using Nyquist theorem.
Yeah, I don't know, Nyquist, I don't know, make up this word? What the fuck was that? Say he's going to put links in the description, they're not there. Whatever that crap is. But anyway, it was showing, so we have a theorem, which isn't much use anyway, that it's not possible to prove the particulate nature of light with normal matter. Well, the two-slit experiment...
That it's not possible.
Okay, the two-slit experiment is not proposed as a way of proving that light's corpuscular. So, I mean, he's just kind of perverting the argument. The only reason why you do this, you attempt, okay, science, physicists attempt to make single photons, is to demonstrate the fact that it appears that it's one wave of light, one bit of photon that is interfering with itself. That there's no rational way you could say that two things could get through the masking screen at the same time and do the whole interference thing. The photons are coming so irregularly that it would be insanely coincidental that every single time you got a signal it was because two photons actually hit an opaque screen and worm their way through it exactly the same phase and exactly the same time. I mean, that would be a preposterous theory. So I don't know what the Nyquist theorem is, but the theorem, your theory, that first the two-slit experiment is proposed as a proof that photons are corpuscular. That's not what it's proposed as. You're merely demonstrating that interference is something that isn't happening because two photons interfere with each other. It's demonstrating that a single photon somehow goes through the device and interferes with itself, some version of itself.
To prove the particular nature of light using normal matter. So first, let's introduce the experiment. Okay, what we have here is a double slit experiment. We have parallel wave fronts impacting two slits.
Let's understand, traditionally it's not done with parallel wave fronts, so all of this stuff that's drawn is just kind of a canard, okay? The Young experiment and all the experiments early done, there was no laser beams, and they used an aperture. So the light first went through a little tiny hole, and then went to the two slits. So the light was already theoretically bowed, okay? It was already diverging by putting it through the tiny pinhole. So not that I think it matters all that much, but this idea that there was straight waves of light is inaccurate. They weren't straight. No, they're not waves anyway. I'm just pointing out the photons were already diverging.
And what happens is you have what's called diffraction occurring, where the waves squirrel out and then they hit the
So again, this idea that the waves swirl out, again, all the, theoretically, what's the grounding for this nonsense, right? Because water waves have friction with surfaces, and the water has tension between the molecules. That's why we know water waves bulge for that reason. Okay, it's because they're dragging against the surfaces. And what's the theory that photons are dragged by surfaces, and that somehow they're made out of a whole zillions of particles they're somehow bound to each other and create a round wave? I mean, the whole thing is just kind of, how do you ground that theory in anything called reason?
the barrier on the side here. Areas where the crests overlap, you're going to get a bright area where the crest falls in between, you know, the peak to trough, you're going to get a dark spot.
Right, so you get an on-off pattern. Now, the trick is so one of the points I would raise is that I just add a few more of these little openings, right? 10 of them, 5 of them, 7 of them, let's say 7 even would probably be enough. And what I'll end up getting is an image here, and an image here, and an image here, and an image here, and an image here. So whatever goes in, I'll get an image of it. So I put an image, you know, the light as an image, into the slits. The light will spread into, you know, they'll spread out much further than those bars, but you'll get the same idea. There'll be a clump and a clump and a clump at distances. And there'll be images. Okay, images that went through the hole. Images. So how, let's see, you know, images that were cast upon the entire slits, you know, however many you had, whatever went to the slits, an image of everything that went through all 7 slits, you know, whatever the image was, that will be reproduced at each location. So whatever it could see, okay, when it went to those slits, that will be projected, and you can see that with a diffraction gradient. So the more lines I make, the more holes, the more slits, the more resolution you have in those images, and they'll be just nice, perfect little images cast at a different location. And if you use white light, then you'll see them perfectly. You'll see the spectra of each one of those images. You'll see each one cast red, green, blue, red, green, blue, red, yellow, blue, whatever you want to call it. So that's a fact. So how do you blend that fact with this interpretation of the experiment? How does interference explain that each one of those bars is essentially an image of the surfaces that it went through?
This is what we call a fringe pattern. Now, there's a great site called Veritasium.
So he says it's a great site, and he calls it Veritasium, and you know it's Veritasium. So you know that always has a little bit of a credibility thing. You know, yeah, I watched one of his videos, and he agrees with what I'm saying, so it's a great site. Maybe not. And again, I would argue that this Veritasium video I've played, it's a piece of crap. In terms of, it's not a great experiment because the noise level was way too high, 50% of the signal.
And the guy's able to show these bright and dark areas using a couple of paddles on a pond. It's really, really good. You should go check that video out. What physicists have done is they've taken this experiment.
So it is kind of funny that he's pointing out, okay, he shows it in water, and then when he actually does the single photon experiment, which this guy's critiquing as being stupid, you know, he gets a pattern that's pretty crappy. Now, this pattern is basically going to, you know, see, this is the part that's sort of annoying, right? They convert through a photomultiplier the photon into an electron signal and then turn it back into a photon again. Now, what sense does that make, right? Because we know electrons and photons are fundamentally different, and whatever resolution you might have had with the photon, you're going to lose a hell of a lot of resolution when you start using these little soft, pushy little electrons that have a force field around them, that don't collide into each other, that go around, you know, bounce off of each other's forces. So you get a nice smooth pattern, you get these nice smoother bars, but it's a complete illusion because the photons wouldn't create that. That's an electron pattern, not a photon pattern. The electrons have rounded the surfaces.
Where they put a laser beam into a double slit and then into an image intensifier into a CCD camera. Now, it might be hard to see from up there, probably is.
I think he's going to show the image intensifier eventually, but that word should just be, say, into an electron converter, okay, that takes photons, turns it into electrons, and then turns it back into photons. Bad idea.
It's hard to see. I don't think my printer has a resolution. But over here, there's only about a dozen green points of light. And what they've done is they have to, that's for one frame. So they take 200 frames, 1,000 frames, 5,000 frames, 20,000 frames, and up to 500,000 frames. And you can start seeing the double slit pattern, what we call the...
All right, so this is Journal of Physics number 2 something. You know, it'd be nice if there was a YouTube video of that experiment actually, but you know, I'll have to try to find that because at least it's, you know, yeah, well, see, no, there's really no point in finding it, because again, they've converted photons into electrons, and you're going to lose all of the detail of the signal by converting little tiny things into big giant things, and then back into little things again.
Double slit fringe pattern. Okay, but the problem with this experiment isn't that you get the double fringe pattern. The problem is they put in attenuators in here. They're intentionally dumbing down the light so that they can come up and show you these couple of points over here and say, aha.
Right, well, they're dumbing down the light because it's, so he says attenuators. It'd be better if we had just regular jargon. So they're putting in black film, layers of film, of opaqueness. And they're trying to get whatever their light source is, they're trying to knock it down so much that only 1 photon a second gets through it, that kind of thing. So they can do this time-lapse thing and get almost a single photon going through the machine at a time. So that, number one, eliminates noise, and it demonstrates that this is a phenomenon not created by a bunch of photons energizing the system, that it's happening to each individual photon is making this voyage, is elemental to the function, in the sense that whatever's causing the effect causes it for every individual photon. The number of photons going through the experiment is irrelevant to the effect.
These are photons, and I'm going to show you that is completely wrong. Okay, there is another variation of the experiment where instead of using a photomultiplier or image intensifier.
So it says link to be posted. There ain't no link. So yeah, I would like to see this one. I mean, not that these are very good high resolution. I don't know what kind of stuff they used, but I mean, and it demonstrates sort of my point that the light to dark is not in the ratio it should be. These shouldn't be big, thick white bars and then little thin black bars.
They just put photographic film here. And with a very, very short exposure time and attenuators, they get a couple of points hit. And then as they allow the film to integrate, you know, the longer you leave film going, the more it integrates. They end up getting back to a solid double fringe pattern. I'm going to show you that this particulate nature of both of these means of detection are a property of the detection means and cannot be attributed to photons.
Right, but this would be true for every single experiment you do with photons. So he's sort of implying that this is, you know, some narrow point he's making. But this doesn't just apply to slit experiments or any of that. This just applies, generally speaking, to the nature of photons. And at the end, he actually says that, in the sense that he gets to the point, which is you need something smaller, you know, to detect something. You have to have your ruler. He even shows a ruler measuring shoes, uses examples. I mean, I'm not going to play the whole video. It's a half hour. Yes, your measuring device has to have a scale that's smaller than the scale of the thing you're measuring, right? So if all you had was inches on your scale, then everything smaller than an inch you'd call an inch would be stupid, you know, because there's a whole bunch of stuff smaller than an inch. And yeah, well, the problem is with detecting photons is we can only detect a certain minimum amount of energy, and that's it, minimum amount of momentum. So it's hard to create an experiment to prove that there's nothing below what we detect, and to say that a photon is this certain amount. Now, the opposing argument I would present is that we do know that it's a certain amount of momentum. So if we don't attenuate the light, we know a certain amount of momentum is coming off the bulb. There's a certain amount of energy. And in lots of experiments, they can account for that energy, like a solar panel or this or that. They can account for where the energy went, how much of it turned into heat, how much of it was converted into electricity, and how much. So knowing how much actual momentum there is something they can do, and then they can sort of, by being careful in doing an experiment, they can know that they're getting 10% of the energy or 20% of the energy, and that this is a pretty reliable. The thing they're doing is actually not losing too much energy in the process of measuring the energy, so that you're getting some, maybe not a perfect equal sign, but a proportional to sign measurement of the travel of the photon, the travel of the momentum. You're just trying to detect where the momentum went. And the truth is, the two-slit experiment is fairly good at detecting where the momentum went.
And I'm going to do that with the Distinti palm tree wave detector. Assume you have a tropical beach with palm trees lining the beach. And then if a high enough wave comes in, a strong enough, powerful enough wave, you're going to clear cut all these palm trees away, and then you have your detection that a wave occurred. But if we do what the physicists do, and we put an attenuator down so that the wave coming in is like much smaller, so that any given wave can't knock over a tree, well, eventually, after maybe, you know, thousands or even millions of smaller waves.
Right. So now the problem with this kind of argument is to get the pattern you're getting with the two-slit experiment, the argument would have to be is that two trees in different locations got knocked down at exactly the same time, and that the energy went through two trees. So this doesn't really defeat the single photon argument in the two-slit experiment, if that's what he's attempting to do. And again, arguing that the two-slit experiment isn't a great way to prove that light is corpuscular or a wave isn't going to work either, because that's not what this experiment is designed to do. You're not using single photons to prove that single photons are corpuscular. You're doing it to prove that single photons can create the pattern.
Waves coming in, eventually you're going to have enough beach erosion that a tree that is more susceptible, maybe an older tree or a sick tree or a tree that has an infestation, maybe a tree that gets with a little bit of wind, you know, kind of like noise, one tree might fall due.
Right, this would still prove the point. Like I said, if you imagine a wave coming off that one tree going to the slit, then you're basically saying that yes, one wave goes to the two-slit experiment and creates a spot in one of the locations on the wall, indicating that single waves interfere with themselves, so to speak. So it sort of just proves the point that you don't need multiple photons interfering with each other. You just need a single photon, a single wave. So it's not multiple waves coming through the device, it's just a single wave. So I mean, I think he's reading way too much into what is being demonstrated by the two-slit experiment using single photons. All it's being demonstrated is all you need is one of those flat waves to hit the wall, and you'll have a pattern. You don't need multiple waves at different phases going through the machine. You just need the one wave.
Due to wave action. But again, that's going to take millions or thousands. This is like exposure. If you have one big bright wave, you knock them all out. If you have very small waves, you know, you have to take a much longer exposure before your wave conductor can detect that you have waves coming in. The problem here.
So again, this is just sort of a canard, because we also know that you can create these attenuating substances where the attenuation is it either blocks the photon, or the photon passed through as if it was transmitted, as if like transmitted through glass. So you either transmit a photon or you don't transmit it. You know, it's a pretty on-off kind of a system. So this is again kind of a, I don't know.
Is the light waves coming in have done such a gradual, slow work, you've only lost one tree.
All right, well, let's go ahead here. This tree analogy is pretty useless, so just jump ahead a little bit.
Videotape this right now, or video this right now. A CCD camera has, let's say, a 60 cycle frame rate, which means its exposure time is a 60th of a second or less.
Well, and it doesn't really matter what its exposure time is. We know that it has a minimum capacity also, that you can make the CCD camera also highly sensitive, and then you'll end up with the same problem, is that, you know, it'll start doing a lot of sort of false signal. That is, it'll be catching a lot of light that we don't see, or that may not be light, might just be, you know, x-rays and other crap that hits the device, and it's going to amplify any energy. So all the infrared, heat, all kinds of stuff are going to create false signals. So it gets too noisy. So it has to be toned down, so it only catches the big hunks of photon, the big rays. So again, this whole conversation is just broken by this really horrible language, and the fact that they decided to call these things waves, and waves don't give you any idea that the waves come in rays. You know, that there's a number of times I poke my finger in the water, and then I stop poking my finger, and there's a certain amount of wave, and that's it. And it goes quiet again, you know. And there's no words or verbiage in the language they've created to get to the concept of a array of waves. You know, a longitude of waves. I mean, there's just no word for, yeah, I poke the water 6 times and there's 6 waves. You know, there's no language for that. And it's fundamental to this whole idea of what you're detecting. It's fundamental. It's elemental. And there's no conversation about it. We don't even have words to describe it, besides me saying array of specific length.
So if we take a single frame of the CCD camera, that's 1/60th of a second. Let's assume they're using red light, which has a very, very long wavelength, and that's 700 nanometers.
Well, let's understand, 700 nanometers is not very long. It's 0.0000007 meters. No, it's not very long.
And speed of light, we'll just round it to 3 times 10 to the 8 meters per second. So the length of light being integrated by this system for any given frame is 5 million meters of light.
So again, I don't know what he did here to create this notion that there's 5 million meters of light, besides do something silly like multiply the speed of light times the frequency of the light and assume that every ray of light is infinitely long or something. What? You know, what is that? Show me that in a formula. What did you do there? Because it doesn't make any sense. So yeah, number of waves. He did. That's exactly what he did. He just went 5e times 6, whatever that is, divided by this incredibly small number to come up with some kind of silly word, and that's all it is. It just this is whatever this is. This is a silly pile of math.
5 million meters. The number of wavelengths for this is 7 trillion wavelengths. So you're saying that we have 7 trillion wavelengths hitting our detector, that we only detect 12 photons?
So again, he's using the frame rate of the camera, which is totally irrelevant to how much light is coming in. So that doesn't mean anything. I just don't know where he got this from. What bizarre contrivance is this? Clearly, the camera sitting there saying hit me, and in the 60-second frame rate, the 1/60th of a second, it's gets hit by 10. You know, so what's complicated? I mean 10 rays. The rays could be 10 momentums worth of energy at that wavelength. That's how much you could fit in that amount of time. That's how many could possibly hit you if one ray started and ended in that tenth of a second. But that's all it's telling you. It's just telling you how many clumps, rays, big enough for me to detect, hit me in 1/60th of a second. What's so complicated? What does that have to do with any trillion crap? There's no trillions in that.
Really? Really?
No.
That's insane. But you know what? Let's do this. Let's go and see what one of these image intensifiers look like. Oh, well, okay. They sort of gate these things with a 100 picosecond gate. Okay? That doesn't really help us, because even though you're gating it with 100 picoseconds, you're still integrating over the 60 hertz frame rate. But even then, with a 100 pico...
you know, the gating voltage is just has to do with the setting up the electrons to jump, and so yes, it's so much higher than the camera's detection rate that it can't possibly have too much of an influence in terms of how many photons it's going to destroy or how many fake photons it's going to create. It's just another way of limiting some of the noise.
Picosecond gate, you still have to integrate 4,000 wavefronts. 4,000 wavefronts. Okay, and here's the other problem with this, is here you have this plate. This is your photocathode, which has got electrons that are being energized by light, and then what you're going to do is put a very, very high voltage, negative voltage on this side, which is going to cause them to say, hey, I don't want to be here. So you're almost helping them jump off, and then what happens, they're going to jump.
Yeah, well, that's exactly the point, is to make them jump based on hitting them with a tiny bit of energy. That's the whole point. Photons have a tiny bit of energy, and you're trying to detect it. That's the only way you can detect it, is to create something, to create a system that's so delicate, a house of cards that's so delicate that all I have to do is, you know, puff at it from 10 feet away and it'll fall over. And that's all you're trying to do, is create a house of cards, creates a cascade event that you can see. So I could be 10 feet away from the house of cards, I go, and I can see it fall down. I can say, ah, that was an event, a puff hit it. Perfectly rational mechanism. But again, converting photons into electrons is like converting bicycle impacts into car movement and then back into a bicycle impact. It's, you know, you're going to lose a lot of your precision in the fluffiness of the big giant things moving tiny distances over the energy of the photon. So you're really going to cut down. You're going to get a much blurrier, duller image. It's still going to have the information in it. It's just going to be blurrier. So when you go from little thing to big thing and then back to little thing, you've essentially blurred your detail.
Jump into these microchannel plate where they're going to bounce around, causing other electrons to bounce out until you get a flood of electrons hitting the phosphor screen, which is where you get the green dot that's seen by the the CCD camera. Okay.
Yeah, the capacity to represent a location accurately with this device seems pretty improbable. So again, the reason why you're blurring the image. So the electron's not going to have any of the locality precision of the photon. It's just going to do a rough approximation. Yeah, the photon was basically in this area. So you took something that had a little discrete, you know, location, and you basically turned it into, yeah, it's somewhere in this area, it's somewhere in this area, it's somewhere in this area. That's, you know, you're just knocking the information value down quite a bit using an amplifier. So here he gets into a lot of photo papers and how photographs
Go and look.
work.
I'll put the link down for it so you can look at it in closer detail. Look at the 200 frames.
Yeah, you didn't do that.
And you'll see down in the nulls, you'll see there's spots down in the nulls in between where the what do you call it, the wavefronts are peaking. That is clearly an indicator of noise. This,
Yeah, well, in the photographic plate experiment, it wouldn't be an indicator of noise, in my opinion. It'd be an indicator of the photons that just don't get affected because they go dead straight, through the device, and they go at divergent angles. So again, the light's not coming through at some perfect flat angle. The light has a little bit of angularity in it when it gets to the slit. The photons are much smaller than the slits, and so they're all coming in at some angles, and some are going to get affected because they go close to the slit, and some are not going to get affected by being far away from the slit. And the ones that aren't going to get affected are going to end up hitting locations that aren't going to be very representative of the overall probabilistic outcomes. They're going to be improbable photons, but they're still real photons. They're just improbable ones. Not too many will take that path. You could almost argue that some of those could be ones that actually do hit the surface of the slit. So you have the slit, and some actually hit the surface and refract and end up in those locations. So you'd expect some noise just from any device that's going to try to measure something, because there's little unlikely events that still exist.
My friends, is the one done with film. Film doesn't have a noise problem, so you can see down in the nose it's complete black from top to bottom. Complete black from top to bottom.
Yeah, so again, I think that's sort of a quote mining the evidence. There's one that's not, and there's one there, and there's one there, and there's noise in the picture. So it's not much noise. So what do you complain about?
Except possibly for this guy here, which an error in the photographic emulsion. Every place where there's supposed to be a null, it's complete black. No noise. If you look at the one from the photo intensifier, you see noise. And in this...
Yeah, well, again, the photo intensifier, you're going to see noise because it's blurring the image. So of course it's creating noise. But you can still see the pattern. The only purpose is to get the pattern. They don't care. They don't need precision. They're just looking for a pattern. That's all they need to prove their point. Is there's a pattern or there's not a pattern. They don't need it to be 100% perfectly detailed. They just need, you can see it.
This one here, at the 20,000 frame, it's hard to see from the camera, but there's a sheen of noise over a cast of noise over the entire frame. Okay, this is certainly...
I would argue there's more of it as you're getting to the periphery. So these would be the more of the idea would be is you'd have more noise for the very eccentric photon. So the more eccentric you're getting, the more diverged you're getting from the straight path, the more likely it is you'd have noise. That makes sense.
Certainly not this area over here. This is certainly what engineers would expect from noise. Okay, and if you look at the one you compare...
Alright, so again, I don't even know what he's trying to prove here, but anyway, so this was sort of interesting going into, here's a good image of talking about photographic film. Where the hell was it? Yeah, the test pattern one isn't really good there. So that's an image of photographic, like it's not the negatives in a 35mm camera, but it's the kind of stuff, the silver shit you would use in a plate, a photographic plate. And he was pointing out how it's different sizes because that allows for an averaging that in some ways creates more information than less, which I don't really understand entirely, but because it allows there not to be a system of complete on and off, where you need to I don't know, it's probably too complex an idea for me to have to explain. But that it would actually make sense to have different sizes of resolution to ensure that locations that have a high probability in a certain location are represented. If they were all just on and off, all you could get is once it was triggered, once it flipped to on, that's it, you're done. You can't see anything else. It already turned on. You hit it again, it ain't going to turn on again. You hit it again, it ain't going to turn on again. So if you have pieces of varying size, then you can get an image that has more of a that's more time exposure. So essentially it has more. I would argue that almost has more to do with the speed of the film than anything else. That it's allowing the film to get a representation in time of the image by having different size particulates that can only be exposed by getting hit by more photons. That now you're allowing the image to show you not what happens in 1/1,000,000th of a second, but what happens over a half a second.
Gives film an incredible dynamic range so amateurs can take decent pictures. And what's interesting is that the larger the grain is, the more susceptible the grain is to very low light levels. In other words, it doesn't take...
See, that's not, it's saying that backwards. It's making it more susceptible to averaging over time rather than just being on and off in an instant. So it's just giving the film a broader amount of time to take the picture.
Take a lot of wave fronts to turn this grain on, as opposed to a tiny grain takes a heck of a lot more wave fronts to accumulate enough energy to turn that pixel on, or that
See, I don't know why he's saying that. It seems totally unintuitive. The small grains are harder. No, they're less likely to get hit than the big grain. But the grain means that it has to be hit more than once, the grain size, to turn on. So that's what the grain size is allowing, is to be variance in time. Have some bits that are instant on and have some bits that take a little bit of time, and that way the average of those two things will give you a more representative image.
Grain on. Okay, and that's why you get a much more grainy appearance with film in low light. If you ever took a movie that was filmed in the 19...
See, I think this image is actually made with an emulsion that tried to reduce the grain size, so they were all the same grain. That's why it's so on and off. That's why it doesn't have any gray tone.
1940s and 50s. Put it on, get it on a high definition medium, like a 4K DVD, and put it on a high definition television set. Go look up close and look off into the corners where it's dark, and you're going to see all kinds of things that look like ants running around. That's the grain of the film, and it's grainier at low levels because of this intentional structure of the film that was designed to give film a great dynamic range. Now, what do I mean by dynamic range? Well, if they made all the film grain in the film exactly the same size, this is what photography would look like.
Yeah, it would only look that way though if we're incapable of controlling shutter speeds and apertures and all that stuff. So you can obviously use other mechanisms to control how overexposed your image gets. But yeah, you still got to allow for the vagaries of what's going to be at a specific moment in time, and you have to say that there's an averaging thing. Everything needs to be seen for what it does over an average amount of time, not any one instant of time. So if you do an instant, yeah, you might get that. But as long as you have some averaging of a collection of moments, then each moment will have a little different tone, and that's where you'll get more shading. So if you took 1,000,000 pictures like that, or 1,000 pictures like that, and superimposed them on top of each other, in terms of, you'd have to have it like that they add, instead of being all on and off again. You can't just put it on and off, but they'd have to add to each other to create an image in the end. Then it would be each one of the black and white images would be different, and subtly different, and when you added up all those subtle differences, you'd have a picture that had much more resolution. This is probably stuff not necessarily needs to go into. So again, here's the foot argument that was really the only argument he made that was semi-useful.
If you want to quantify audio, that when audio range is 20 to 20,000 hertz, you must sample at 40,000 hertz at a minimum to be able to reproduce the sound with enough quality. And let me give you an example using shoe size. Suppose your ruler for measuring feet only had 1 foot and a 2 foot index, and that's all you had. That's the granularity of your measuring instrument. You either get a measurement that's 0, 1 foot, or 2 foot from your measuring instrument, nothing else. How good do you think it would be for you to put shoes for a kid or an adult? It would be horrible. You would go out of business being a shoe salesman. But if you had a measuring instrument that had much more granularity, you could get shoes much closer and be a much more successful.
Right, and that's sort of getting the granularity is doing the multiple frame rates. And in a sense, even the electron experiment, creating a bunch of electrons that are easily popped, is a way of creating a over time average where you can see above the noise, because there'll be some level of influence, and so you're measuring a thing much smaller than the energy it would take to move the electron. You're just creating the puff that knocks down the house of cards. So in some sense, the experiments are attempting to create an artificial granularity to their measuring device, give it some sort of capacity to measure this very small stuff. But yeah, I mean, there's always going to be a limit to what you can measure. The smallest thing is going to be hard to dissect because there's no knife sharp enough. So yeah, that's a fact. But it's not a fact that gives you liberty to say that nothing comes in clumps. Because we can't measure clumps, there's no clumps. Well, that's going too far. Alright, so he's basically just making that argument over and over. I thought he'd give this, I haven't read this Wikipedia page, but I think he'd give it pretty short shift. So I think I'll go find that.
That's all bullshit.
So he's basically saying all these devices that measure photons or energy using different techniques.
Photodetectors configured to detect individual photons, which is complete nonsense, because I've shown you before it takes thousands or millions of waves combined with noise to finally get one of those electrons to bounce.
Right, so he's saying it's thousands and millions. There's no evidence there's any reason to believe that at all, so I don't know where he gets that from at all. That's just crazy talk from as far as I'm concerned. What experiment demonstrates thousands or millions of waves? No. And there's lots of experiments, again, that sort of indicate there's a pretty reliable amount of energy required for a photon to do a certain thing to an electron. And, all the evidence sort of points to that you can do this minimum amount of energy that we can measure is pretty small, blah, blah, blah. And if we do experiments over a long period of time, you find out that yes, over a million of these events, there'll be a certain average that comes out of it, and those experiments aren't complete nonsense. So, like I said, this is just this is a way too generalized statement to be making.
Then the photon, that's hard to see. We can imagine if you're trying to, you can't see, let's say you can't see the basketball. Okay, let's say basketball represents matter. But if you had very small particles of light, let's say light were made of photons, well, you could take that light and bounce it off the basketball and eventually shoot enough pieces of ping pong balls around, and even though you couldn't see the basketball itself, you would be able to see where the ping pong balls bounce off of and be able to take a good measurement of what you're trying.
Right, so he's clearly not seeing it the way I am, that the only way you bounce this basketball out, the whole point is of the photoelectric effect is that you can't just bounce it out by hitting it with infrared ping pong balls. You can throw them all day at the wrong frequency and they're not gonna bounce the ball out. You have to hit them at the right frequency to bounce it out, and that means the ball has a resonance, and you have to hit with its motion. And if you hit it with its motion, you will magnify the stored energy and you will eventually get the ball to bounce up. So it's the same idea. If I want to pop a ball, bounce, you see professional basketball players can do this stuff without even trying. They just poke the ball with their fingers and the ball goes up and they can start dribbling. They don't have to pick the ball up or some other bullshit. they know how much energy it takes and how what the resonance of the ball is, and they can just knock it with their knuckles and start dribbling the ball. Well, that's the same thing. They're hitting the basketball at the right amount of energy, the right velocity, to create perfect compression that pops it all up at one time, so it doesn't waste the energy by compressing too slowly and then rising too slowly and all that kind of stuff. It bounces back up at the right. You get more energy out of in one form straight up, instead of in, you know, expansion and contraction of the ball. All right, so it's probably enough of a video, right? I don't know. He just makes a lot of statements here, and I don't even know what his underlying argument is here. Besides, clearly he thinks photons are made out of whatever, some sort of whatever stuff that's going all over the place or something. I don't even know what his argument is.
So you're not looking at photons. You have not proven photons.
You know, again, it's just a statement, doesn't mean anything. There's clearly a certain amount of energy delivered in a certain amount of time, so that part, if you're going to argue that momentum is an illusion, well, no, that's not an illusion. Now, what we define as a photon, yeah, that's garbage. Our language is broken because we're still using an archaic vocabulary to describe something that has way more detail in it now, and you just can't call it earth science or something. It's not a rational category.
Okay, we can only make conclusions about the structures that are larger than the resolution of the detection devices. In other words, you can't attribute anything to an individual pixel that is turned.
So again, it's just wrong to say that you can't see a pattern, take a pattern of ping pong balls, throw that pattern at a bunch of basketballs, and realize the pattern at the end in the basketballs. Of course you can. Patterns don't get destroyed. Now, obviously, how much resolution, how much detail you can see, that changes. But the fact that there was a pattern going in and a pattern going out, that you can tell.
All you can look at is say, oh yeah, through all this noise, I do see that we have periods of absence of pixels and periods of waves coming through, and that we do have a.
Yeah, I don't understand how you even think that I have periods of waves coming through. That doesn't look like waves to me, right? I don't see a wave anywhere in there. Okay, waves aren't on and off, on and off, on and off, going sideways. So just none of that makes any sense. It doesn't look like waves. Little dots don't look like waves. Newsflash.
We do have an interference pattern.
Says you. All right, so now he's P.T. Barnum quotes, which I don't think he was a highly qualified physicist.
Gravity, which I'm starting now, is going to replace general relativity. And please get the word out about this experiment. Go to all the places where they start honking about the particle wave duality and the photon, and just start saying, no, you guys got to see this video by this crazy Distintian.
Yeah, how did you resolve the duality question? Where did you prove it's a wave? I mean, you didn't prove a wave. You merely stated that the two-slit experiment doesn't prove that photons come in corpuscles or clumps. Well, that's not what it's intending to prove. It's just merely intending to prove that whatever this pattern is, it's not happening because you send a bunch of waves in. It happens one wave at a time. So I don't know how you disproved what the experiment is intending to prove, and you clearly didn't prove that photons are waves. So anyway, now it's enough of the video. Alright, so till the next time and such. But there's so many flaws in the two-slit, as I pointed out, but the one that really screams to me at the moment as being the one that people should get is the fact that, yeah, if I make more slits, it becomes clearer and clearer that the things at a location are actual images of the light that went in. So every single, that it matters. Let me draw that. I'll try to. I get a little better camera because this just is too small an area and it's too hard for me to find the drawing area. I need a You need a bigger screen. But the idea would be is that if you have these slits, and let's just do 4 of them for the hell of it. The idea would be is your image goes across all of the slits. So in the 2-slit experiment, if your image is much bigger than the slits, then you're going to just get the bar pattern, because all you're going to really get a picture of, okay, you're not going to get a picture of these rounded edges. You're not going to see any of that. You're just going to get this part of the light. So there's not going to be any rounding or any of that other stuff. So you get nice little bars, which are basically just images of this part and this part. There's no image of the middle. There's just an image of this part and this part, the surface. The stuff that went in the middle just went straight and landed here in the middle. So it's sort of irrelevant. Because obviously the screen is much larger than the size of the slit. So, you know, the slits are only taking up a little fraction, you know, a little one line of this whole thing here. So any light that goes straight through will just be resolved as a tiny speck on the screen. And so you're really just picking up the divergent light at a distance. But all you're getting is the images of the surfaces. So every photon goes in, and it either goes to this location or it goes to this location, but it goes to exactly the same place on that location. So it represents an image location inside the slit. So, sorry. Yeah, I gotta find a better way to draw. It's just, I'm just not doing this well enough. I should just look and see if it's in the damn camera. You have to understand the slit like this. There's a place where the photon hits, and it'll, depending on where it goes, it's still going to be in that same place. Oh, Jesus Christ! Still going to be. Still going to be in that same location on the bar. So it's not going to show up over here, you know, on the sides. It's going to show up in exactly a representative location. So no matter where it lands, it's going to be in the same location. So if it goes to this place instead, it's going to be in the same exact location that it was here. So this is going to be represented here. And so the point would be is that if you have 2 slits, and your laser beam is the same size or smaller than your 2 slits, then what you end up with is a bunch of circles as a pattern, because you're getting the full images of this light is what's going through the slits, hitting the slits, and so the roundness part is being reflected in the location, so it's representing the image. And as I stated, if you have multiple slits, this is where it really shows up, is if I have a bunch of slits and then my image covers all of those slits, and I just make my image have a pattern in it, you know, then I'll get my pattern at the locations. I'll get a representation of that pattern, which means that each individual photon has a location where it went through, and it's representing that location. So there's no interference happening, because that would wipe out any of that information. So unless somebody's got some reasoning or theory they can apply to explain how interference wouldn't wipe out that location information, but that's clearly what's happening, in my opinion. That the fact that a diffraction gradient demonstrates that overtly, that the image is transferred wherever it goes into the slit, the same pattern goes to the target, just an enlargement. So a little hand goes into the slit, big hand ends up at a location, and the same hand ends up at each location, because depending on the chance of when the photon went through a certain location, it either gets bent once, twice, 3 times at this angle. So the same location at any different time in time, as time changes, each location changes in what it could be. So going through here, this location on the slit, say if there's a slit here, and I go through this particular location, well, at 1 second that location might mean you're diffracted 5 times. You know, you go way over here. The next second you go to the same location, you might end up over here. The next time you might end up over there, because all of this these electrons, the surface is active, and it's changing the device, it's shaking it all the time, shaking it, shaking it, shaking it, Brownian motion, shaking it, shaking it, shaking it. So each time a photon goes through, it's going to move it's going to go to a different location, but each time it goes to a different location, it's going to be the same finger. You know, so if this finger goes through over here, it's always going to be a finger there, it's always going to be a finger there, always going to be a finger there. And I think that's a proof, a theoretical, logical proof, that this theory of interference is the wrong answer. Added up with all the other proofs, like the single slit still isn't explained. Why does the wave break into two? The fact that the photon pattern isn't the nice gradual on-off pattern it's supposed to be. It is. It has every appearance of being images of whatever your slits are made out of. So you can just add up all these facts and say that's a lot of evidence indicating this can't be the right theory. Wave interference. It's not the right theory. It's wrong. And it's been wrong for 100 frickin' years. Well, it's been wrong for 200 frickin' years. No, it's been wrong since Newton, since frickin' Huygens, who I have to admire. Huygens was really brilliant. Made fantastic clocks and stuff. Really clever person. But it was just a stupid idea. This stupid wave theory of light was stupid. There's nothing you can say. I mean, like I said, Tesla wasn't an idiot. It's just that he had a couple of brain farts that were just so magnificently huge that, more bad than good. Alright, so now we're done. So, till the next time, and such.